This is Jack Jackson. In this video, we're going to be doing an example of a one-sample two-tailed z-test. We'll be using calculator technology with this, actually a TI-84 calculator, but it would work similarly with other technologies. So the question that we're going to consider is, in 2005, a report determined that the mean amount of television watched by Americans was 4.55 hours per day, with a standard deviation of 2.31 hours. We want to test this amount of television watched by Americans now as different than this. We take a random sample of Americans and determine the following amount of television per day for each person sampled, and we get this data here. Perform a test of hypothesis to determine if the current amount of television watched by Americans is different today than in 2005, and use alpha equals 0.1. Let's also assume here, I think I got it on this slide but not the previous one, that the distributions is approximately normally distributed. So the first thing we want to do is determine what sort of test would work here. Now, first note that this is a one-sample, two-tailed z-test, and why is that the case? Well, first of all, we're testing for a difference in mean between a single sample and a hypothesized population. That makes it a one-sample test of means. It's two-tailed because we're concerned with any difference in mean, including either an increase or a decrease. So we're going to be looking at critical regions or probabilities on both tails. The distribution of individuals is normal, or at least approximately so, because we assume that the distribution of individuals is normal, so regardless of the sample size, we get the distribution of sample means to be normal. With the sample size of, well, if you count these, there are 20 of them there. Sample size of 20, we could get by with something less than normal, but it needs to be, free of too many problems like not heavily skewed and so forth. The population standard deviation is also given to us as being known. So those are the conditions that we need for a one-sample, two-tailed z-test. Next, the thing we want to do is find the sample size and the mean. Of course, we can just count the number of data points, which is 20, to get the sample size. To get the mean, we just add these up and then divide by 20. We can do this together at once in our calculator by going to Stat, Edit, and then clear list 1, type in the data in list 1, then go to Stat, Calc, number 1, one variable statistics for list 1, and it tells us our X bar, our sample mean is 4.735, and our N is 20. Now right away we see that 4.735 is larger than 4.55, so we see a difference in mean there, but the question is that difference in mean significant enough? Is it a large enough difference from the hypothesized mean that we think that this is very likely to be because people are watching more television now? Or is it just because there's a difference that you would normally expect from doing sample to sample and getting sample means each time? Well, which is it? Hypothesis testing allows us to quantify that. So that's exactly what we're doing with hypothesis testing, is putting a number to that. So we want to state the null and alternative hypothesis. So the null hypothesis is that the mu is 4.55. So we're going under the hypothesis that the mean of the population is 4.55, and furthermore, we're going to assume that the distributions of sample means is approximately normal, and so we'll base our calculations on that. The alternative hypothesis is that mu is just something different than 4.55. And notice again, just reviewing, we have n equals 20, the standard deviation of individual x's is 2.31, and the sample mean x bar is 4.735. Next, we compute this test statistic. Now, this is a standardized test statistic. In other words, it's a z-score. So we standardize it by taking the x bar we found, subtract the hypothesized mean, so that's x bar minus mu naught, and we divide by the standard deviation. But this is the standard deviation of the x bars. Remember, the standard deviation of the x bars, sometimes called the standard error, is the standard deviation of individuals divided by the square root of the sample size. So that's sigma sub x divided by square root of n. Plug all those numbers in the formula right here. You can see how I typed it in the calculator right here on the right, and we see that it's 0.35815, etc. And it's probably useful to store that as z. Notice in the calculator I went ahead and stored that as z, so I don't have to type all these digits in again later. We only want to round off our final answer. We want to leave all the digits we have in the calculator, since we have those, and we'll get a more accurate answer that way at the end. Next, we have a choice. We can either go to the critical value method or we can go to the p-value method. And I'm going to actually do it both ways, and we'll see that we get the same conclusion. So the critical value method, what we have to do is we have to find the critical values corresponding to the alpha levels that we were given. And then, since this is a two-tailed test, the probability below the lower critical value is alpha over 2, and the probability above the upper critical value is also alpha over 2. So together, the two critical areas together make a probability of alpha, which is our threshold that we're willing to accept for a type 1 error. Now, since the test statistic is, since the z-scores are distributed by a standard normal curve, we can just compute one of the two critical values and then take its opposite sign for the other one. So I just went ahead and just took alpha and divided by 2. 0.1 divided by 2 is 0.05, and did an inverse norm of that. That's going to give me a negative number to the left of the mean of 0. And then the opposite of that is the other critical value. So those are our two critical values there, about negative 1.64 and positive 1.64. Again, notice here's our z star, over here our test statistic. And what we want to do is we want to compare our test statistic, z star, to these critical values. And let's just go back again. I'll illustrate this with a picture in a minute or two here, but basically what happens is that the z star is closer to the mean than these critical values. It's in the non-rejection region. And if it's further away from the mean than these, it will be in the rejection region. It'll be one of the tails. Well, notice that 0.35 is not that far from the mean. It's certainly between the two critical values here. So that's the non-rejection region. There is not enough evidence to reject the null hypothesis. So we failed to show that there was any difference. The data did not support that, or at least not any significant difference. Now, let's illustrate the p-value method. To find the p-value corresponding to the test statistic, we do that and then compare it to the actual alpha value. Now, notice that the critical value method was comparing, basically x to x or z to z, and this is the p-value method is comparing probability to probability, p to alpha. So the way this works is you just find the probability associated with that z star statistic. So the p-value is the probability of getting something at that level or further out, more extreme, in this case further away from the mean, if the hypothesized null hypothesis is actually true. So what we do is we take our z star value that we'd already found, and by the way we stored it as z, and we just do a normal CDF from z out to infinity will be the area to the right. Now notice the z is positive, z star is positive, so that means that that's the boundary on the right tail. Now since this is a two-tailed test, that's only going to be half of the p-value. So we have to double that to find the p-value. So we get p is 2 times normal CDF of z star to infinity, or this is our z star value. Instead of infinity on our calculator, we can put in, since it's a standard normal, we can just put in 10 and 0, 1, and that gives us our p-value. Notice this is absolutely equivalent to just using our x bar value up to infinity, or mu naught plus 10 sigma, roughly. And finding that with the mean and standard deviation here of sigma of x is divided by square root of n. And notice either way you do that, this second way or this first way, you get the same probability value out of your calculator. I did it here on the calculator. See, I stored z as the 0.358 whatever. I did 2 times normal CDF from z to 10, 0, 1, and that's my p-value. I've already doubled it here. Over here, another way to do it is I went ahead and took 2.31 here divided by square root of 20 and stored that as s. That's the standard error or standard deviation of the x bars. Then I just did 2 times normal CDF x bar up to, well, actually I just did 10 here. I probably should have still done mean plus 10 standard deviations, but it still turns out to be the same thing. That's close enough. basically you want to put infinity there or something. You can't put infinity, so you put something big. Now let's illustrate the picture. Oh, well, let's make the conclusion before we illustrate the picture. In the p-value method, the way you do it is you look at the p-value and compare to alpha. In this case, the p-value is bigger than alpha, and so definitely 0.7 something is definitely way bigger than 0.1. So there's definitely not enough evidence to reject the null hypothesis. So there's a picture associated with the critical value test, and there's a picture associated with the p-value test. We could actually do this on our distribution of the x-bars, or we can do that on the z-scores of those distribution of x-bars, which is what I've got here. So this is a standard normal curve here and here. And the picture with the red stuff at the top, the boundary here are your critical values. So this 1.64 or something is the boundary right here of the upper tail. And the opposite of that, negative 1.64, is the boundary here. So that each of these two red tails have an area of 0.05 or probability of 0.05 there. Total those together, you get alpha, which is 0.1. Then you find your z-star value, which is right where this vertical line is here, and we see it's most definitely in the non-shaded region, so it's do not reject. The p-value approach is you find the z-star value here, then you just find the probability of something more extreme than that. So you go to the right of that to get this blue shaded region, do the mirror image over here. Each one of these is well, about 0.36. That is p over 2. Together they add up to about 0.72, which is the p-value. And so we see that that's bigger than alpha, so we fail to reject. So the conclusion is the mean time spent watching television by the individuals in this sample is 4.735 hours. With a p-value of 0.72 and an alpha of 0.1, there's not enough evidence to support the conclusion that the average time spent watching TV has changed since 2005. So note that although the mean of the sample is higher than the hypothesized mean, this difference is not large enough for us to conclude that the mean of the population has actually changed. A sample such as this, with this size mean, is extremely likely if the hypothesized mean of 4.55 is what people are still watching. So in fact, the probability that you would get something this size or further out is 72%. That's a pretty big probability. So we do not have enough evidence here to reject the null hypothesis. Notice that when you state your conclusion, it's very good to include the sample mean, the alpha level, and especially the p-value level, and then put it in context of the problem. So it should be some sort of sentence or sentences in context of the problem.